Hi class, hope everybody is doing fine. I'm sorry for the late notice. I wanted to record this lecture on gesture recognition and post it so you can start thinking about how to use interesting machine learning techniques for gesture. So gesture recognition is also, uh, an example of the body of work in machine learning, which we are sort of touching upon. The techniques that get used in the recognition of gestures sometimes are similar to the techniques that get used in recognition of images and pictures. And there is a variety of methods. So we want to talk about a few methods here which are robustly implemented in Max MSP. There are neural network models also for recognition of gestures, but we are not going that far. We are looking at some classical robust methods like dynamic time warping, trajectory matching, and hidden Markov models and what they can do. In terms of immediately available tools, I will highly encourage you to look at a package called MUBU for Max, MUBU for Max, and I'll share my screen soon, and I'll post the links for it. I would not be surprised if it's already a package in the latest distribution of Max 8. But if not, here is, let me share my screen. Let's look at Firefox. I hope you see this. This is MUBU for Max from IRCAM, which is a very famous institute in France, which does a lot of interesting things in real-time gesture, sound, video synthesis with movement. And we tend to work quite a bit with their toolkits. So MUBU for Max is a toolbox for multimodal analysis, sound, motion, interactive synthesis, this and that. It's usually available for free. If not, if you don't find it for free, let me know. But I remember finding this, it was free several years ago. So the gesture follower is one of the signature toolkits of this distribution, and we will walk through some examples as well as the techniques that lie behind it in today's class. So the gesture follower toolkit lets you record time series of presumably movement or gesture, and it converts it classifies the movement into one of 3 or 4 different classes that you have to train it to recognize. It's a very nifty tool to trigger certain things based off of some specialized gesture. So if you're in the middle of designing an interactive performance, you want to trigger some sound effect when you do a very special move, you can train the system to do those things. It's not magic, so we'll talk about many of the assumptions that go into how to make it work. Okay, I'll break it down. It's not it's involved. Mathematics is complicated, but I'll try to keep the discussion at a high level. Let me show you some examples first so you can see what's possible. Okay, so let me share my whole desktop. So we will look at 2 examples. So if you download MUBU for Max, it will come in a folder like this. Oh, where did it go? So MUBU for Max, there will be a ton of examples, documents, and externals. Look in the examples subfolder, and this other thing in it called GF. GF stands for gesture follower, and you'll see a few examples. We will look at 2 of them, which are easy to understand. The first one is mouse to audio Max patch. So when you open it, let me clear it. When you open it, it will appear this way. And the way this is set up is the big LCD object. This is the LCD object on which you can draw stuff, but you can also connect external movement data to be plotted on this LCD if needed. Okay, so this is not the only way you interact with gesture follower. The way it's set up is you take mouse input, but you can recode it to take external sensor input. And then the way this one is set up is you train the system to recognize 3 gestures. And based off of which gesture you use, it will trigger 1 sound. So the first thing it asks you to do is, this is a help file, drag 3 sound files into the 3 boxes on the left, or you can record your own special sounds. So I don't know what you want to do. Feel free to play with it, but I want to keep it simple. So we'll just drag and drop a few audio files from the Max audio, library. So let's look at a trumpet sound. Oh, I don't know if you can hear stuff. So let me stop share and share with sound. Share screen, share sound. Okay, so here is one sound file. Trumpet residual.
对不起，我能跟你说几句话。
Let's take talk. Talk is very distinctive. I want 3 very distinctive sound files so that you can appreciate when the gesture follower is switching between the sounds. If you choose 3 very similar sounding things, you won't even be able to tell if it's doing anything. And then, okay, next, let's look at cymbals and maybe a clap. I like the cello, so let's take the cello as the second sound. And drum loop. Oops. Okay. Some pop music. So I've dragged these 3 sound files, and now I'm going to record 3 different gestures which will trigger the 3 of these sounds. So to do that, there is a protocol here. You say learn one, and it will latch on to the first sound file and the gesture that is supposed to trigger it. So actually you will, when you start using gesture follower, you will find that it's actually very difficult to even identify 5 unique, significantly different gestures you can do with your hand or a finger. Of course, you can draw, you can start writing alphabets. You have 26 alphabets to write. Sure, you can do that. But if you want to be a little more natural, it's not that easy. I mean, how many different contortions of the hand could you do? But we will try. I'll try the first gesture to be just circular movements. Okay.
对不起，我能跟你说几句话吗？
Okay. So I'm going to train the first sound to be recognized by just a cyclic circular motion. Then I go learn 2. And my second gesture, I want to use, let's say, a wave pattern, a sinusoidal wave pattern. So I go like this or something. So I go. Okay. So this is my second. I go wave and I come back. The third pattern, the third gesture that seems somewhat natural to me is maybe a zigzag movement. Okay, so I go zigzag. So I go. Okay, this is my third gesture, so zigzag movements. And now I say follow, and now I clear it. And now when I start doing, so remember the cycle, the circle was the first one, the sinusoidal was the third one, the second one, and then the zigzag was the third one. So the thing to look for, there's a few things. There are a few indicators on this panels that are there for you to just debug. So the first thing you want to see is these traces on each of the sound files. You have this red trace and this little light blue, whatever, red and blue, which are the X and Y coordinates, the raw traces of the X and Y coordinates of your movement as you were doing it on this LCD panel. So the first thing to notice is the XY traces themselves look different across the sounds. If the XY movements look very similar across the sounds, you're going to have trouble. It's not impossible. Again, what looks similar or dissimilar to you, to your eye, is not the same as what looks similar or dissimilar to the algorithm. Okay, so don't mix up your visual perception with what an algorithm can tell. But sanity check, if you're doing this for the first time, choose 3 very different looking gestures. So clearly, yeah, the cycle, the sinusoid, zigzag seem very different visually, and also it's reflected in the XY traces that you can see. This is very different than this and from this. Okay, good. And then the second thing you want to see is these vertical bars that you're seeing, which actually indicate the probability. It's a measure of probability in any classification problem in machine learning techniques. When you start digging into some of the mathematics, you will see that most machine learning techniques will never be able to conclusively say what the input is, whether it is gesture follower, whether it is using neural nets for object recognition, whether it is whatever. The output is always going to be a confidence measure, a probability. I think this is this gesture with a high probability, a higher probability than these other 2 gestures. So the numbers are going to be always going up and down. So this is an indicator of probability. So right now when I do nothing, the 3 bars look roughly about the same height. So the system is not sure what I'm doing. It's just saying it could be one of these 3 with equal probability. And as I start doing more, one of these bars is going to rise higher than the others. And the way this patch is set up, it will pick up the maximal, the highest bar, and play that sound. If you're doing confusing gestures, you can expect things to be roughly, equal. Maybe at least 2 of them will be roughly equal, and it won't be very clear what will happen. So let's just to break the system. We had cycles, sinusoids, and zigzags. I'm going to test it with a 4th gesture, which I didn't train it on. And that 4th gesture is, let's say, just a straight line. I just draw a straight line for whatever it's worth. See what it does. Okay, so it began with roughly equal probabilities, and for some reason it is choosing to map it to this guy. It seems like zigzag. It's interpreting my first move as maybe the first section of, I don't know. It's interpreting this as a rough sinusoid, which is interesting. I didn't expect it. Let's do an infinity sign. Okay, so it could be, this is complicated. It has some cyclic nature. It has some sinusoidalish nature. It also has a zigzag nature. So it's getting pretty confused, right? This is gesture recognition. So let's not break it. Let's do it the way we trained it to. So the first thing I do is cycles. That works. Sinusoids. Okay, that works. And then zigzag. I forget if the third sound was that bad. So anyway, the bars look about right. The orange bar on the third is the highest. So this is the way you would actually work with it in safe ways. The problem with any pattern recognition thing is when you give it unknown inputs, you train it to recognize 3, but there's an infinite amount of gesturing you could do. If you constantly run it, the system will force itself to categorize whatever you're doing into one of these 3 bins. That's the way the whole thing is set up. So if I start doing alphabet A, okay, it will still do something to it. So this is the problem of classification and recognition. If you let it just run all the time, you will see that it will do unexpected things simply because the space of inputs is too many, and classification is limited to 3 or 4. So when using gesture recognizers like this, it's important not to run them all the time, but to run it intentionally at specific times when you know that if you're a performer, let's say, you know that now is the time you want to do your special gesture, somehow have other triggers in place that prime the system that, okay, now start paying attention to the gesture that you're doing. Don't pay attention to the gesture all the time, because if you do that, it will constantly keep mapping your gesture to one of these 3 things. So it's important to have that at the back of the mind. What the tricks that people have used in the past is they train the gesture follower like this, but they won't ask it to recognize until you hit a switch, or you have some other trigger, or you use your, if you have motion capture, maybe the right hand is what is doing the gesture, but the left hand is what is triggering the on-off switch for the gesture follower to turn on. So think of these ways in which you want to control the gesture follower from turning on. Good. So here is another example of the same technique. I already sort of trained it. The way this is set up is it learns, this is like mapping gesture to video. What we just saw was mapping gesture to audio, but you can imagine the possibilities are limitless. When you click learn, it's using your webcam to record a piece of video. As you're doing the gesture, it records the video that is playing on your webcam, and that is what the output will be when you do the gesture again. So again, if I do infinity signs, this is one video that will get recorded. The second one is, let's say, It says zigzag patterns. And I want to do a different way. I want to put my hand on my face. Okay, let's say. And I go zigzag. Okay, now follow. So now when I do my infinity signs, okay, that's odd. Okay, it's playing some video, and when I go to my zigzag, it plays the video with my hand on my face. And when I go to my infinities, so it looks like the infinity and the zigzag have some common features, as we already sort of suspected. Infinity is a complicated thing. It shares traits of sinusoids and zigzag patterns, so not a very good input. So simplifying, circles and zigzag, and follow, circles and zigzags. Oh, I didn't. Zigzags, follow, circles and zigzags. Okay, so this is converting gesture to video outputs. Okay, cool. So how do these things work? Let me go back to my presentation. Close, 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 close. So the way these things work, and I have this Prezi, my only Prezi ever made, which I would love to share with you, because a class on movement has to have some movement. So the way any of these things work, these gesture recognizers and most things to do with gesture, if done well, they are basically fancier and fancier ways to compare time series to other time series, or trajectories to other trajectories. So let's just play. Oh, I don't want to start with that. Why is it going straight to this? Oh man, okay. Okay, let's go to the very beginning. Sorry, beginning. Okay, play. All right, so the goal of, trajectory matching and as applied to gesture is basically you're making a trace of some kind, either on a screen, it's a two-dimensional series of points, or if it's motion capture, it's a three-dimensional series of points, or if it's your wearable device, you have 6 degrees of freedom, it's a 6-dimensional series of, feature vectors, whatever it is. You try to compare, when you record it, you have this time series recorded, you want to compare it with something else that is being played at runtime, so to speak. And this lecture is simplifying the process to just 2D and 1D time series to give you the concept, but the same concepts apply to other higher dimensional things like 3D motion capture or 6 degrees of freedom, wearable stuff, same concepts apply. The goal is to compare a measure of similarity between a time series and a time series, okay? Now, one of the things, okay, so how is time series represented when you talk of gesture? Typically, as we already saw, when I was making my time series on that LCD screen, it was overlaying my X coordinate and my Y coordinate onto the audio files. So really, that is the basic representation of gesture. It is a time series of coordinates. If it's 2 dimensions, you have X and Y coordinates. If it's 3 dimensions, you have X, Y, Z. If it's 6 dimensions, you have whatever, X, Y, Z, and your pitch roll. So 6 time series. They are sort of written down like that. If I were to compare 2 time series with each other, the most basic beginning point is to compare the distances of corresponding feature vectors in time. So here is how it is. So if you have a time series like this is a trajectory in XY space, another trajectory in XY space. The most basic way you compare how different the 2 trajectories are is you compare at t equals whatever, the first time instant, that point, compare its distance with the corresponding point in the other time series. Then you go to the next time instant, look at the XY coordinate, compare the distance of that point with the distance of the point on the other gesture. So you're comparing point to point distances and adding it up over the entirety of the gesture. That is the most basic beginner's way of comparing gestures to other gestures. I hope that's clear. You're basically comparing a gesture as a series of points You have now two gestures. You compare the distance, the raw distance. Remember the distance formula that we have been working with in motion capture? X minus x squared plus y minus y squared, that's it. So you compare 0.1 on one gesture to the first point on the second gesture, 0.2 on the first gesture to 0.2 on the second gesture, add up all those distances over the entirety of the gesture. That is referred to as the Euclidean distance over the time series. There are problems with it. The problems are several, especially when it comes to gestures. One of the things that people like to talk about is this idea of robust representations and invariant representations of gesture. Meaning, if I looked at this sinusoidal pattern, let's say I'm tracking the tip of my finger and I draw this sinusoidal pattern on my screen or motion capture, and I just rotate around and I draw the same gesture, the XY coordinates, the XYZ coordinates of that gesture will look very different than this gesture, which I drew here, even though it's the same gesture, right? I'm just drawing sinusoidal patterns and here is sinusoidal patterns, but the XYZ raw coordinates will look very different because the location has changed. Do you want to be sensitive to the location of the gesture, or do you want to be sensitive only to the shape of the gesture? First question. Nobody knows. I mean, that's a design choice, but by and large, the field in gesture recognition has settled to a general shared design principle that you want to be sensitive to the shape of the gesture, not necessarily to the location. I mean, my gesture could be 6 feet in the air or 1 feet below me or to the right, to the left, whatever, as long as it's the same shape, I don't want to recognize it as a different gesture, which means I cannot use the raw XYZ coordinates to compare gestures because the raw XYZ coordinates are sensitive to placement of the gesture. So that's what we mean by these things. Translations, rotations, and then scale and warping are different. So by translation, I mean sinusoid at 3 feet, sinusoid at 6 feet. That's translating the gesture up. Or rotating, the sinusoid pointing north versus sinusoid pointing east. It's a rotated gesture. I want to be invariant to these kinds of rotations. Scale simply refers to the extent of the size of the gesture, so to speak, meaning sinusoid, small sinusoid or big sinusoid. Okay, so that is scale. Warping is perhaps the most interesting and most complicated to deal with, which is I can speed up and slow down at different phases of the gesture. I can go fast on some phases and slow on other phases, fast again, or I can go uniform speed throughout. Do I want to be sensitive to the speed, the phasing of my gesture, or do you want to compare them? Do you want to refer to them as the same thing despite speed changes? Big questions in the field of gesture recognition, and there are no silver bullets, but there are a few methods which are known to work well in certain cases and not so well in other cases. First thing, let's talk of each of these things. How do you get invariance? The word invariance means not being sensitive to translations and rotations. So, which means the physical placement of the gesture in space. Where is the gesture occurring? So there are certain tricks which are commonly employed, and many of these tricks are already sort of, implemented in gesture follower. So you don't have to redo them from scratch, but it is important to know what tricks have been employed, so you know the limits of the techniques. So the first thing is, if you want to be invariant to placement of the gesture, gesture at 3 feet versus gesture at 6 feet, I don't want to care where it is in space. One of the things they do is, you can remove the center of mass, which means as I'm doing my gesture, I can sort of average out all the points, and that gives me a center of mass, and I just subtract out the center of mass from everything else, which is okay, but that assumes that you have recorded the gesture fully, or at least somewhat, so that you can get that center of mass. If you have not yet recorded it, and you're just doing it in real time, you don't have a way to estimate the center of mass in robust ways. You can always do a running average. You can say, keep averaging my location over the past, 50 frames, and keep treating that average as the center of mass. You can do those tricks. But there are other ways to do it. But hold on to that. Let's look at rotation. If I rotate my gesture, I go this way versus this way, How do I get invariance to that? Again, center of mass removal will not help. If you remove the center of mass, still the directions are going up and directions are going down. So you want to also have some invariance to directionality of the gesture, in which case people have suggested to look at not location, but angles between or velocity vectors of the gesture and the angles between them. So what I'm showing here are these little blue arrows are your successive difference vectors. So if I have a point XYZ here, another point XYZ there, that little blue line is the velocity vector that connects the 2 points. But the velocity vectors themselves have directionality. So you don't want to use the velocity vectors either. You can use the speeds. Speeds are invariant to direction. Speed is the absolute magnitude of that velocity vector. That is invariant to directionality. But you lose some information. When you only look at speed, you lose some information loss is there. And that information loss has to do with these turns, the curvatures and stuff like that. And that can be encoded by angles between successive velocity vectors. So the combination of successive angles and speeds will give you invariance to rotations. So some of these things are, I provided some references for these papers. Feel free to read them. These are very, specific choices and perhaps not necessary for simple applications, but just be aware that these things are available. Then, okay, shift, let's not worry about this. The other very common trick that people use, gesture follower, for example, uses velocity vectors. I think, that was definitely the way they coded it up a few years ago. I have not kept track of the latest implementation, but the gesture follower toolkit has a paper to go with it. Read it. What I remember reading it, and I also saw the previous implementation in depth, they used, when I had this time series of XY coordinates, they were not using the raw coordinates, they were using velocity vectors to train and test gestures, which means when you use velocity vectors, you already get invariance to placement. Up or down doesn't make sense. You don't get invariance to rotation. If I rotate my gesture, velocity vectors will also get rotated. So be aware of that, it won't work. But then you can encode it other ways. You can change out the velocity vectors and replace it with speed profiles and look at successive angles and retrain it, see if it works. So there's many ways you can advance what they're doing. So scale is very hard. I mean, if you have a small gesture and a big gesture, velocity vectors will look different, speeds will look different. Scale is perhaps the hardest one to get invariance to in real time. I wanted to mention a little bit about time warping because it's something that's close to my heart. We've written a ton of papers on time warping. So time warping refers to, gestures done in different phasing. You speed up certain parts and you slow down certain parts. Why is time warping even of interest? It turns out that if you want to create a system for yourself or for other people to use and you want to train them to make circles, you will notice, there's many scientific studies that have been done which say the same gesture done by different people will exhibit time warping. Different phases of the movement will be done at different speeds by different people. It's just the way their bodies work. And even there are variations within yourself. When you do the same gesture on a different day, different time, you don't do it the exact same way. And one of the most common versions of that variation is time warping. You speed up certain parts and you slow down certain parts. That's just the way the body is. So to get invariance to time warp, there is a set of techniques built which are called time warping techniques or dynamic time warping techniques. Not easy to explain quickly. It's detailed math. The idea is, the first definition we saw of measuring, how do you measure difference between two trajectories? You go from the first point on trajectory one and measure the distance to the first point on the second trajectory, and then you do the second to the second, the third to the third, and then you add it all up. In time warping, you are allowed to not go in such a regimented way, time one to time one. You're allowed to go time one to time 5, time 2 to time 7, time 3 to time 10, time, whatever. So the mapping can be somewhat not time-based. It can go forward in time, but not backward. You can't go backwards in time. So if you have a sequence X and a sequence Y, the thing that time warping is trying to do is to match things like the peaks to the peaks, the valleys to the valleys, peaks to the peaks, and valleys to the valleys. And it tries to do it in a way that the matching arrow is always pointing generally forward in time, and you try not to go backwards in time. So if you go backwards in time, you have to squish the rest of the time series. So it's like stretching and squishing different parts of the time axis to align the peaks and the valleys to each other. The mathematics gets involved. You have to solve a problem, an optimization problem, which is referred to as dynamic programming. I have a reference here, which is from Music Information Retrieval. I encourage you to check it out. It's not easy to unpack it in a small lecture. I mean, even when I do these things in engineering classes, it can take a couple of classes to describe what these things are. But the intuition is you're trying to come up with nonlinear elastic maps between the time axes of two time series. But gesture follower doesn't work with this. There are other implementations. There is other libraries in Max like ml.lib, which actually implement dynamic time warping. I have never tried it. I encourage you to look it up and see if you want to work with it. But let's get to state space models, which is what gesture follower is. So in all of the things that we have looked at so far, we are basically looking at two basic components, which is how do you represent time series of gesture, things like velocity vectors or speeds and angles between velocity vectors, and sort of normalizing it so that you get some invariance to location and rotation. We are doing some simple pre-processing methods. But none of these methods actually construct a model for the gesture. A model means the model so far is really the trace of the gesture itself. So a model is an abstraction. When we say state space models, any word model is a slight abstraction of what you're observing, which can be used to explain many different variations within that space. So a model is not an example. When I draw a figure 8, if you just record that figure 8, you have recorded an example of the gesture. An example is not a model. A model is one level abstracted out. So in the concept of gestures, a model might look like this. If you're drawing a figure 8, and let's say the input representation that is chosen is velocity vectors, the model would say something like, okay, this figure 8 looks like going southwest for some time, going south, whatever, northeast for some time, going southwest for some time. And then you're transitioning between northeast, southwest, southeast in a regimented way. So the model would say, looks like you have 4 or 5 prime states. Okay, that's the word that they will use. And the state here might refer to the 8 directions. Okay, the 8 cardinal directions. I'm just simplifying the whole thing, but just imagine. I say that my model for any gesture is how often do you go along the 8 cardinal directions as according to a velocity vector, and also how do you switch from one cardinal direction to the other, or how often. So if I'm going southeast, the next direction I take for the figure 8 maybe jump from the southeast to going north, right? And then from going north, I come to southwest. From southwest, I jump north. From north, I go southeast. So that is the model of the figure 8. So just try to imagine that 8 cardinal directions, north, south, east, west. I start from somewhere. The first point is go north for whatever time. From going north, I switch to going southwest for some time. From going southwest, I switch to going north for some time. From going north for some time, I switch to going southeast for some time, then going north. So from the 8 cardinal directions, I really only used 4 states: north, south, east, north, southwest. I only used 4 states. So that is the model of the figure 8. I'm not giving you an example trace. I'm saying figure 8 is defined as switching between 4 states. And the 4 states are these. And also there is a sequence to how I switch between the states. I don't go from northeast to southeast. I don't go from north to southeast. I only go from north. The first thing is going from north to southwest, southwest to north, north to southeast, southeast to north. So there is a switching structure, which is also encoded. So that specifies a model for a gesture. When you do it this way, the benefits are the states, right? When you define states, you're basically somewhat coarsely representing the true gesture. So I can do some wiggly north direction, but as long as I'm generally going north, the state space model has to learn to map even that wiggly gesture, which is generally going north, as going north. And then from going, so it gives you some added robustness when you break down gestures into these states. So within each state, there could be variations to how I stay in that state or how I go in that state direction. But you don't always have to be very super specific about what's happening inside the state itself. And that's the way you think of state space models. But of course, the cardinal directions are just an example I cooked up. There is the true hidden Markov model approach is you don't even assume what the states are. You also have to learn what the states are. So here is an example of trying to estimate a hidden Markov model through some scribbling gestures, just like what we were doing. So on the bottom right is an example of a scribble gesture. Now this has been, hidden Markov models are not just used for gesture recognition, but also for gesture analysis in many, many applications. The way you sign your name can be analyzed through these state space models, and depending upon what the model learns, you can be classified as a healthy person or someone who's suffering Parkinson's. We have slightly different models of how the gestures are. We can identify, people have tried to identify styles of movement. You know, hidden Markov models also are used in synthesizing movement for robots, humanoid robots. And I can synthesize it in the style of Michael Jackson or in the style of someone else. So the style of your movement is encoded in the model. So lots of interesting things can be done with hidden Markov models. So this is a generic reference I found, which applied it to studying the scribbling movements in primates, whatever. But the point is, you take gestures like this, time series, and after many such traces, the system learns to first define states. You know, the example I gave you about states was this 8 cardinal directions, whatnot. But the states in a generic hidden Markov model thing would be not defined that way. It would be defined by, you know, short segments of the gesture, short segments that seem to be repeating several times. So if primates are drawing this gesture several times, here are 8 different states that the system has identified as common motifs, common repeating smaller patterns of gestures. So I cannot give linguistic meaning to each of these, but you can see that maybe when the primates are drawing, you know, this little sharp V-shaped gesture, there has to be a state which defines that as a state. So I'm guessing this one, this state, is showing you multiple overlays of that little V shape that people have drawn. So this is a state. You will go through this state while drawing your gesture. How often do you go through that state? And how do you jump from this state to the next state? Defines the model of that gesture. So each of these little plots is showing one specific segment of the gesture, which seems to be repeating, and it's a motif in that gesture. And maybe this little thing is probably describing this section of the gesture several times. If you do that, it looks like this is a repeating motif. Then the arrows are showing the switching structure. How are you switching between the states? The bigger the arrow, the more common is the transition from one state to the other state. So the switching structure doesn't always have to be 1 to 2, 2 to 3 to 4. It can be from 1 to 7, 1 to 8, but the strength of that, the frequency of that transition is represented by the strength of the arrow. So the model consists of the states and the switching structure between the states. And the hidden Markov model learns to figure out what the states are and what the switching structure is. It does that through techniques like clustering and fitting probabilistic models to data. So as you can see, within each state, the movement shows variability. It's not like when I say go north, it doesn't mean going straight up north. There is always some variability in how you go north. And the same thing when I say, look at this V-shaped structure, that V-shaped structure can be done in many different ways, but it looks generally roughly like a V-shaped structure. So there is variability within each state. It gives you added robustness to interperson variation. You know, you can train it for yourself, but the model is generally robust to work with different people. And you can actually train it with multiple people's data, so it gets more robustness that way. Yeah, so that's hidden markup models for you. So now after the model is trained, when you start doing free form gestures, the first thing the hidden markup model does is it takes the gesture that you are drawing right now. Now the HMM is different for different gestures. Remember, we have a different model for the cycles, we have a different model for figure eights, we have different models for wiggly gestures, the zigzag things. Everything will have its own model. When you are doing free-form testing of gesture analysis, your free-form gesture is fed in to each of the three models. When we say fed in, it will try to break whatever you're doing in terms of the states that it has learned and in terms of the transitions it has learned. So if you are feeding a zigzag model to a figure eight, if you're feeding a zigzag example to a figure eight model, it will try its very best to explain the zigzag nature through the states of the figure eight. And if it just cannot find the right state, if your movements do not conform to the switching structure of the model, it gets assigned a low probability. It will never conclusively say that it is not a figure eight. It will say it just seems very, very unlikely that it's a figure eight. And that's the thing. That's why you have those probabilities. So that's how gesture followers work. That's how hidden markup models work. And let me stop sharing right now. And I encourage you to try working with these tools with the things you have. 2D motion capture, variables, 3D motion capture, what have you. See if you can train it to recognize just even very simple one or two gestures, but taking care to work with distinct gestures in the beginning, and don't expect it to do magic. If you keep letting it run all the time, it will just do some crap. So learning how to trigger it at the right times with maybe a different modality can help robustify its use. So think of those things, okay? Thank you so much. I apologize again for the short notice. I have this meeting which is about to begin in 3 minutes. I can't get out of it. And I'll post this video as soon as I'm done. I appreciate it. Thank you.